Hello my dear friends, welcome to my YouTube channel. Myself Dattu Patel, Assistant Professor from LJ Institute of Engineering and Technology. Now we are going to discuss about our new unit of this syllabus, sequence and series. You all are aware about finite sequence and finite series, in which is already studied in earlier standard. Nowadays we will going to expand it infinite sequence and infinite series. Now today's session we are going to discuss about firstly infinite sequence. What is infinite sequence? A set of numbers which is particular orders is called infinite sequence. Here like as u1, u2, u3 up to un and so on, where u1 indicate by the first term of the sequence, u2 indicate by the second term of the sequence, and in general un indicate by the n term of the sequence. Now let's see the notation of the sequence. Basically sequence has two types. First one is infinite sequence, second one is finite sequence. If sequence is infinite, then we denoted as in curly bracket un, where n is running from 1 to infinite. We can also written as in curly bracket un, where n greater than or equal to 1, or simply we can also written as un. If our sequence is finite, then we can written as in curly bracket un, where n is running from 1 to infinite. We can also written as in curly bracket u1, u2, u3 up to un. It is not necessary to sequence which is always starting with 1. That means starting from the sequence may be any value, means like as n equal to 2 to infinite, 5 to infinite, 3 to infinite. Let's see the more examples of the sequence. Here first sequence which is n upon n plus 1, where running from n equal to 1 to infinite. Now here n term of the sequence which is un, that is n upon n plus 1. Now substitute the n equal to 1 in un, then we get 1 by 2, then n equal to 2, then we get 3 by 4, n equal to 2 by 3, n equal to 3, then we get 3 by 4, and so on. Here let's see the graphical representation of the sequence. Here this graph indicate by the n versus 2, n upon n plus 1. Now let's see the second example, which is minus 1 raised to n upon n plus 2. In this sequence un is equal to minus 1 raised to n upon n plus 2. In this sequence substitute the value of n equal to 1, then we get minus 1 by 3, n equal to 2, then we get 1 by 4, n equal to 3, then we get minus 1 by 5, and so on. In this sequence first term which is negative, second term which is positive, third term which is also negative, means our term has a alternating sign, means positive, negative, positive, negative. Then we can say that this type of sequence is called alternating sequence. Let's see the graphical representation of the given sequence. Here in this graphical representation, some of the points which is above the x-axis and some of the point which is below the x-axis. Below point which is negative, above point which is positive. Here this graph indicated by the n versus minus 1 raised to n upon n plus 2. Now let's see the one more example of this sequence, which is cos n pi by 2, where running from n is equal to 0 to infinite. Here n terms of the sequence un equal to cos n pi by 2. In this term substitute the values of n equal to 0, then we get cos 0, then value of cos 0 is 1. Substitute the n equal to 1, then we get cos pi by 2, then value of cos pi by 2 is 0. Now substitute n equal to 2, then we get cos pi, value of cos pi, that is minus 1, means our sequence is 1 0 minus 1 0 1 0 minus 1 and so on. In this graphical representation the sequence which is n versus cos n pi by 2. Now let's start with our limit of sequences. Firstly, with the help of epsilon delta limit definition of limit, we can find the limit of sequence. A sequence un has a limit L, we can written as limit n tends to infinite un equal to L as n tends to infinite. If every epsilon greater than 0, there is a corresponding integer n such that small n which is greater than capital N, then modulus of un minus L, which is less than epsilon. Now let's see the basic properties of the limit. Here there are two sequences which is un and vn are convergent and c is a constant. Then first property, which is in terms of addition form, means limit n tends to infinite un plus vn equal to, now separating the limits, then we get limit n tends to infinite un plus limit n tends to infinite vn. Similarly, second one limit which is in form of subtraction form, then limit n tends to infinite un minus vn equal to, now separating the limits, then we get limit n tends to infinite un minus limit n tends to infinite vn. Now let's see the third property, which is limit n tends to infinite c into u of n. Now in this property, c which is constant, that is comes out from the limit, then we get c limit n tends to infinite un. Now third property, which is in terms of product form of the two sequences, then limit n tends to infinite un into vn, then we give the limit individual sequence, then we get limit n tends to infinite un into limit n tends to infinite vn. Similarly, our two sequences are in form of division form, then we get limit n tends to infinite un by vn equal to limit n tends to infinite un by limit n tends to infinite vn, if denominator portion must be not equal to 0. Last property is limit n tends to infinite un raised to m. Now inside the whole bracket, limit n tends to infinite un whole bracket raised to m, where m greater than 0 and un greater than 0. Now let's see the some standard limits. These are the following limits which is used to finding the example, means you have to remember it to solving the example. Firstly, limit n tends to infinite ln n by n equal to 0. Secondly, limit n tends to infinite 1 plus 1 upon n raised to n equal to e. Similarly, limit n tends to infinite 1 minus 1 upon n raised to n equal to 1 upon e. Next one is limit n tends to infinite nth root of n equal to 1. Fourth property is limit n tends to infinite x raised to n equal to 0 if mod x less than 1. Similarly, same manner, limit n tends to infinite x raised to n equal to infinite where mod x greater than 1. Next one is limit n tends to infinite x raised to n upon n factorial equal to 0. Now next topic, which is convergent. Firstly, what is convergent? So a sequence un has a finite limit, means limit n tends to infinite equal to finite as n tends to infinite, then we can say that our sequence is converges or it is convergent. Let's see to better understanding, we give the one example. Test the convergence of the given sequence which is 2n minus 2 upon 2n minus 7 upon 3n plus 2. Firstly, whatever the sequence which is our un, then un equal to 2n minus 7 upon 3n plus 2. Now applying the limit n tends to infinity to the un, then we get limit n tends to infinite 2n minus 7 upon 3n plus 2. Here in numerator portion and denominator portion, we are common n and cancel out, then we get limit n tends to infinite 2 minus 7 by n and 3 plus 2 by n. Now substitutes the n as a infinite, then anything upon infinite we can say that it is 0, then we get 2 by 3 which is finite. If our limit is finite, then we can say that given sequence is convergent. Now let's see we discuss about the divergent. Firstly, definition of divergent. So a sequence un has a infinite limit, or we can say that more than one limit, then limit n tends to infinite equal to plus or minus infinite, or we can say that more than one limit as n tends to infinite, then we can say that our sequence is diverges or it is divergent. Let's see the one more example to better understanding the divergent. Test the convergence of sequence which is 2n plus 1. First, whatever the sequence which is given, that is indicated by the un, then un equal to 2n plus 1. Now applying the limit n tends to infinite to the un, then we get the infinite. If our limit is infinite, then we can say that our given sequence is divergent. Now let's start with some basic theorems of the sequence. Firstly, theorem 1. If limit n tends to infinite mod of u of n equal to 0, then limit n tends to infinite u of n equal to 0. Let's start with one. counter example for better understanding. Then limit n tends to infinite minus 1 raised to n upon n if it is exists. So firstly, limit n tends to infinite mode of minus 1 raised to n upon n. Here minus 1 raised to n has a value minus 1 or 1, that is depends on value of n. If n is even, then we get 1. If n is odd, then we get minus 1. If we applying the mode of minus 1 raised to n, then minus sign will be negligible and we get 1. Then we get limit n tends to infinite 1 upon n. Now n as a apply the limit n as a infinite, then we get 0. Therefore according to the theorem, we get limit n tends to infinite minus 1 raised to n upon n equal to 0. Now let's see the one more theorem of the sequence. If limit n tends to infinite un equal to L and here f is a continuous function, then limit n tends to infinite f of u of n, then we apply the limit inside the function which is f of L. Let's understand with one counter example. Limit n tends to infinite sine of pi by n. Here sine is a continuous function. Then we apply limit n tends to infinite. Then limit n tends to infinite sine of pi by n. Here sine is continuous function. Then limit comes inside the function. Then we get sine of limit n tends to infinite pi by n. Here apply n as a infinite. Then we get anything by infinite, that is 0. Then we get sine 0. Then value of sine 0 is 0. Now let's start with one counter example. Limit n tends to infinite e raised to 2 by n. Here e raised to 2 by n, that is indicated by the exponential function. Here exponential function is always continuous everywhere. Now we applying the limit in exponential function, then limit will be goes to the in exponent part. Then we get e raised to limit n tends to infinite 2 by n. Now applying the limit, then we get e raised to 0. Then value of e raised to 0 is 1. Now let's see the examples of the convergence. Then first example is test the convergence of the sequence in curly bracket un upon un plus 1. In curly bracket indicate by the sequence. Then our n term which is un equal to n upon n plus 1. Now applying the limit n tends to infinite, then we get limit n tends to infinite equal to n upon n plus 1. Now we have to common n in denominator portion and numerator portion. Then we get limit n tends to infinite 1 upon 1 plus 1 upon n. Now we applying the limit, applying the n as a infinite, then we get 1 upon 1 plus 0. Then we get answer is 1, which is finite. Therefore our sequence is convergent. Now let's see the one more example of the sequence. Is the sequence n square plus n upon 2n square minus n is convergent. Now our un is equal to n square plus n upon 2n square minus n. Now applying the limit n tends to infinite to the un, then we get limit n tends to infinite n square plus n upon 2n square minus n. In this example, n square which is common out from the numerator and denominator, n which is cancel out, then we get limit n tends to infinite 1 plus 1 upon n, and denominator portion has a 2 minus 1 upon n. Now we apply the limit n as a infinite, then we get the 1 by 2, which is also finite answer. If our limit is finite, then we can say that given sequence is convergent. Now let's see the one more example of the convergence, which is our sequence which is in curly bracket 10hn. Here h indicated by the hyperbolic function. You all are aware about basic trigonometric function or basic 6 trigonometric quantity, which is sine, cos, cosec, cot, tan, etc. Now similarly we have a basic 6 hyperbolic function. Here h indicated by the notation of the hyperbolic function. Let's see the here in bracket, that is the definition of sine hyperbolic function in terms of exponential form. Here sine hx, which is indicated by the e raised to x minus e raised to x by 2. Similarly cos hx, which is indicated by the e raised to x plus e raised to minus x by 2. Now suppose we have 10 hyperbolic function, then 10 hyperbolic which is sine by cos, cos hyperbolic, cot hyperbolic which is cot by cos by sine, etc. Now our sequence which is un equal to 10 hyperbolic n, then we applying the limit n tends to infinite to the un, then we get limit n tends to infinite 10 hyperbolic n, then we have the basic hyperbolic function of the sine and cos, then convert into sine and cos, then limit n tends to infinite sine hyperbolic n upon cos hyperbolic n. Now substitute the formulas of sine hyperbolic function and cos hyperbolic function, and 2 which is cancel out, then we get limit n tends to infinite e raised to n minus e raised to minus n upon e raised to n plus e raised to minus n. Now simplify this term, then we get limit n tends to infinite e raised to 2n minus 1 upon e raised to 2n plus 1. Now in this term e raised to 2n which is common and cancel out from the denominator and numerator portion. Now limit n tends to infinite, then we get our term is limit n tends to infinite 1 minus 1 upon e raised to 2n 1 plus 1 upon e raised to 2n. Now apply the limit n as a infinite, then e raised to infinity that is infinite, then 1 upon infinite that is 0, then we get 1 minus 0 upon 1 plus 0 which is 1. Now our answer is a finite, then we can say that our sequence is convergent. Now let's see the one simple example of this sequence which is 2 raised to n. Then here 2 raised to n, that is our n term. Now applying the limit to the un, then we get limit n tends to infinite 2 raised to n, then apply n as a infinite, then we get 2 raised to infinite which is infinite. Here our sequence is infinite, then we get our sequence is divergent. Now let's see one more example, show that the sequence cos n pi by 2 is divergent. Here our un equal to cos n pi by 2. Then we apply the limit n as a infinite, then limit n tends to infinite un equal to limit n tends to infinite cos n pi by 2. Here we don't know exactly infinite which is where the exactly end point. Then we consider as a this one is a unitary circle. Then first one here suppose angle is 0, n equal to 0, then value of cos 0 that is 1. Now we go through the pi by 2, then cos pi by 2 that is indicated by the 0. Again we go for cos pi, that is also value minus 1. Again cos 3 pi by 2 that is 0. Again 1, 0, minus 1, 0, 1, 0, minus 1, 0. Means here our limit of this sequence which is not unique, means we can say that it is divergent. If our limit of sequence is not unique, means we have multiple answer, more than one answer, means 1, 0, minus 1, then we can say that our sequence is a oscillatory sequence, that is the part of the divergent. Now let's see the one more example of this sequence. Does a sequence whose the n term which is an equal to n plus 1 upon n minus 1 raised to n is convergence, then find the limit of that term. Now here an equal to n plus 1 upon n plus n minus 1 raised to n. Now applying the limit n tends to infinite to the our sequence, then limit n tends to infinite n plus 1 upon n minus 1 raised to n. Now in this term n raised to n which is common out from the numerator and denominator portion, and it is also cancel out, then we get limit n tends to infinite 1 plus 1 upon n raised to n, and denominator portion 1 minus 1 upon n raised to n. Then according to this standard limit we can say that limit n tends to infinite 1 minus 1 upon n raised to n equal to e, and similarly replace positive sign with the negative sign. Instead of positive sign we get negative sign, means limit n tends to infinite 1 minus 1 upon n raised to n, that is 1 upon e. Then we substitute this value, then we get e upon e raised to minus 1, then simplified that term, then we get e square, where e square that is our finite answer. Then we can say that given sequence is convergent. If you have any doubts regarding this topic, then feel free contact me. Thank you so much for patient listening. If you like this video, then don't forget to subscribe my YouTube channel.